Today we are going to talk about 9 different types of functions and their graphs. There are many different function types, but these 9 are some pretty common ones. So first we're going to talk about a constant function. So a constant function in function notation is f of x equals a, and a is just for a number. Okay? So not a variable, but some actual number. So for example, not in function notation, it would just say y equals, and maybe y equals 3. So that's a horizontal line, up 3. No matter what the x value is, the y value is 3. Okay? It's constant because the y value is a constant number. It is not changing. An identity function, f of x equals x, or y equals x, which means whatever the x value is, the y value is the same. So if x is 0, y is 0. If x is 1, y is 1. If x is 2, y is 2. And so on. So an identity function looks like this. A square function, f of x equals x squared. So it's a parabola. So if I have 0 squared, I got 0 as my output, 1 squared is 1, 2 squared is 4, 3 squared is 9, that goes off the graph, but I'm still going to put a point there, approximately 1 off the graph, because otherwise I don't really know where I'm heading once I get past this point, so that just keeps me on the right track. Negative 1 squared, negative 2 squared, and negative 3 squared. So that square function graphs as a parabola. A cube function, f of x equals x cubed. 0 cubed is 0. 1 cubed is 1. 2 cubed is 8. Negative 1 cubed is negative 1. That third power, odd power, does not get rid of that negative. It's negative 1 times negative 1 times negative 1. Still have a negative in my output. Negative 2 cubed is negative 8. Now, just like the square function, and I didn't really say it up here, but it's a curve that we're graphing. So we need to make sure that it actually is a nice smooth curve. So on this cube function, we're going to do our best when we get toward this middle just to make a nice smooth curve. And I kind of missed my point up here, so I'm going to try that again. It's important to try to be precise as we do these graphs. Okay, so we'll be as precise as we can while we do these graphs. A square root function, f of x equals the square root of x. By the way, that's the same as x to the 1/2 power. A square root does not allow negatives underneath, so there will be no negative x's. So zeros and bigger. The square root of 0 is 0. The square root of 1 is 1. The square root of 2, it is a real number, but it's not an integer, so I'll continue. Square root of 3, no. Square root of 4 is 2. The next one is the square root of 9, which is off the graph, but if I want to know where I'm going, I need to graph it. Square root of 9 is 3, so I'm going to plot that approximately just to make sure that I keep going in the correct direction. So that is a square root function. An absolute value function, f of x equals the absolute value of x. The absolute value of 0 is 0. Absolute value of 1 is 1. The absolute value of negative 1 is also 1. The absolute value of 2 and negative 2 are both 2. So we can see a V shape forming. On the right side of this piecewise function here, we've got a slope of 1. On the left side, negative 1. A rational function. Rational with that root word ratio. It's a fraction. F of x equals a number over x. Okay, so for example, you could have y equals 4 over x. Okay, so if I use 0, 4 divided by 0, well, that's undefined. So that means that the y-axis, where x is 0, we're never going to touch that with this graph. So that is going to be an asymptote. If I do 4 divided by 1, I get 4. 4 divided by 2 is 2. 4 divided by 4 is 1. That's not really enough to tell me everything I want to see, though. If I do 4 divided by 8, 4 over 8 is 1/2. And if I do 4 divided by 1/2, I get 8. That's going to give me a little better story here, what this graph should look like. Okay? But I can use negatives. I can't divide by 0, but I can divide by a negative. 4 divided by -1 is -4. Divided by -2 is -2. Divided by -4 is -1. 4 divided by -8 is -1/2. 4 divided by -1/2 is -8. So it reflects over y equals -x. And it looks like that. So as it goes off to the right, up, left, and down, it hugs the axis. An exponential function, f of x equals a number to the x power. So let's do an example of y equals 2 to the x power. So 2 to the 0 power, just like anything to the 0 power, is 1. 2 to the first power is 2. 2 to the second power is 4. 2 to the third power is 8. So you can see that with each interval to the right, it's getting steeper, going up faster. 2 to the -1 power. So 2 to the -1. If you remember your rules of exponents, I can move this to a denominator. So I'll put that over 1, and I can move that 2 down into the denominator, and it becomes a positive exponent, leaving me with 1 in the numerator and 2 in the denominator. So 2 to the -1 is 1/2. Okay, now I don't have the precision here to really do any closer to y equals 0 than that. So this graph looks like this, and y is never actually going to reach 0. It's going to hug that axis, and it's going to get infinitely close to 0. So the x-axis here, where y is 0, is an asymptote. A logarithmic function. For the purpose of what we're doing here, this one will be the least precise graph that we make. Log base b of x. So we can think of this in terms of y. Instead of function notation, it would be y equals log base b of x. And if I put that into exponent form instead of log form, I've got a base b, exponent of y, and an argument of x. If I put in a 0, any b to the 0 power is always 1. Anything to the 0 power is 1. So if y is 0, x is always 1. So that point right there, 1, 0, is definitely going to be on this graph. And as it goes down this way, it's going to hug the y-axis. And this is where we'll be less precise with this one. It goes off in that direction. It's very important that we become familiar with each of these types of functions, their equations, and their graphs as we go forward throughout this unit and farther in this in pre-calculus.
All right, now we'll finish up this lesson with some review about how we test for different types of symmetry within a function. So for number 1, we want to determine whether this function has symmetry with respect to the origin. So it would be rotational symmetry about the origin. Okay, there's a name for that. It's called an odd function. So we want to know if this is an odd function or not. So to determine that, the test is that f of the opposite of x would have to be the same as the opposite of f of x. So f of the opposite of x is 5 times -x squared plus 6 times negative x plus 9. Negative x squared is exactly the same as positive x squared. Anytime there's an even exponent, that negative will be able to go away. So it's 5 times x squared, and then 6 times negative x is negative 6x plus 9. And that's all the simplifying we can do there. The opposite of f of x looks like this. Negative, and then f of x, 5x squared plus 6x plus 9. And I can distribute that negative and get negative 5x squared minus 6x minus 9. This and this, they are not the same. So the answer is no. It does not have symmetry with respect to the origin. It is not an odd function. Then for this next function, we'll determine if it has symmetry with respect to the x-axis, the y-axis, y equals x, y equals negative x. It could be all four. It could be any combination of those. It could be none of those. Okay, so the four tests we're going to do are for the x-axis, the y-axis, y equals x, and y equals the opposite of x. For the x-axis, if there's symmetry about the x-axis, that means that this particular function's graph could flip vertically. That means that for every x that exists, for every y that exists, the opposite of y also exists. So to test for symmetry about the x-axis, we negate the y's. Negative y squared equals 4x squared over 9 minus 4. And then we determine if we can algebraically make that equal to the original. Negative y to the second power, that's an even power. That is exactly the same as positive y to the second power equals 4x squared over 9 minus 4. And that matches the original function. So yes, there is symmetry about the x-axis. If there's symmetry about the y-axis, then we know that this function could flip horizontally over the y-axis. And if that's the case, then for every x, the opposite of x would also exist. So we can say y squared equals 4 times the opposite of x squared over 9 minus 4. Can we algebraically make that equal the original? Well, we have negative x squared, and again, that's an even power. Even powers cancel out negatives. Y squared equals 4x squared over 9 minus 4, and that does match the original. So yes, there is symmetry about the y-axis. Symmetry about y equals x. Okay, so that's symmetry over this line right here. And when there's symmetry about y equals x, then for every x and y, you can switch them and that point will show up. So I can switch the x and the y. So I have x squared equals 4y squared over 9 minus 4. So the question is, can I algebraically make that match the original? So what I'm going to do is make one side match the original. So what I'll do is get y squared by itself and see if that matches this right side. So to get y squared by itself, let's move that 4 to the other side. I have x squared plus 4 equals 4y squared over 9. Okay, then I can get rid of that 9 by multiplying both sides by 9. So I have 9 times x squared plus 4 equals 4y squared. Then I can divide both sides by 4. Okay, so let's distribute this at the same time. So I get 9x squared plus 36. Okay, then I'm going to divide by this 4 equals y squared. All right, I've got y squared by itself. Now, if I simplify will it match this original on this side? So 9 over 4 is just 9/4, so I get 9x squared over 4, and then 36 divided by 4 is 9. Okay, so does that match the original? Y squared does, but this other side does not. There is not symmetry about y equals x. Then symmetry about y equals negative x. So that's symmetry over this line. For every y, the opposite of x exists, and for every x, the opposite of y exists. So I should be able to switch and negate the x's and the y's. So y squared becomes negative x squared equals 4, and then x squared becomes negative y squared over 9 minus 4. Can I algebraically make that match the original? Negative x squared is the same as positive x squared equals 4, and then negative y squared is y squared over 9 minus 4. And at this point, I've got exactly the same thing as I had right here. So I can follow all the same steps and end up right here, and it's not going to match the original. There is not symmetry about y equals negative x.